Okay, good morning, Evan. It looks like it's just you and I currently. I'm not sure if everybody else decided not to come because they didn't want to do any review, because that's really all we're doing today. So if you have any specific questions or things that you want me to go over, you can throw your mute off, or you can feel free to just put it in the chat. If there's something you want me to do some example problems of, I have no problem going over stuff. You got to let me know though.
Yeah, for sure.
What's up?
I guess we could just go over the last two tests, just kind of what we did last time.
Okay. So one of the things that I think gives people a little bit of trouble is that third test. So that was like chapter 6, 7, and 8, which was
Yeah.
all on like calculations using moles and moles to grams and all those sorts of things. Do you remember that section?
Yeah, I remember that section. It was pretty hard for me.
Okay, so let's just let's go over some stuff, okay?
Okay, awesome.
So let me share screen so you're not just staring at my face. There we go. Okay, so I think the first thing that I want to do, I'm just going to write out that flow chart again. This was for all the chapter 6 stuff. So
Okay.
we can calculate grams of an element. Okay. We can convert that into moles of an element by using molar mass. All right, so this is molar mass. Specifically molar mass of the element. So if it's for carbon, you need to use the molar mass for carbon. If it's aluminum, you use it for aluminum. When it's an element, you don't have to like add up or calculate anything. You just use the straight number off the periodic chart. When we're going from moles of an element into number of atoms, that's where we use Avogadro's number. So Avo's number, which was 1 mole of anything is equivalent to 6.022 times 10 to the 23rd individual pieces of it. So if you've got a mole of carbon, it's equivalent to 6.022 times 10 to the 23rd carbon atoms. Also, let's put a second row in here and put like a compound of sorts. So grams of a compound can be converted into moles of a compound. And we do that using the molar mass of the compound. So this one you're going to have to calculate, meaning you have to add up all the individual elements that are within a compound. So let's say we had Fe2O3 as our compound. If I was to calculate the molar mass, I need to take the mass of 2 irons and 3 oxygens, right? And add those together to get your total molar mass. So it's an extra step when it's a compound. And then we can also go from moles of a compound into molecules of a compound. So number of molecules. Hey, Elizabeth. We're just starting to work on chapter 6 stuff. So getting that flow chart together. So this is also Avogadro's number, because, right, Avo's number says 1 mole of anything. Doesn't matter if it's an element or a compound. 1 mole of anything is 6.022 times 10 to the 23rd. Individual things, or in this case, individual molecules. And we can add a couple bridges to go between moles of one thing. So moles of a compound to moles of an element. And this is done using the subscript of whatever the formula is. You can also do that here, the subscript, and I'll show you in a second an example of that formula. So let's go back to that Fe2O3 compound. If I wanted to know, like, or make a bridge between moles of the compound and moles of the element, well, this formula is a mole relationship. So what this thing is actually saying is that if I have 1 mole of the compound, in this case it's Fe2O3, that is going to yield, or it needs or requires 2 moles of iron. Where is that 2 coming from? It's coming from right here, okay? This 1 mole of this will also yield or require 3 moles of oxygen. The 3 is coming from this area right here. So this concept is what bridges between the element and the compound. We put an X here because there's no easy way to go from grams of an element to grams of a compound or vice versa. You have to do a multi-step problem. Is that good so far, Evan and Elizabeth? Clear
Yeah,
as far as the setup? Okay, so let's just do some example problems now. I'm not going to tell you where you're starting or where you're ending on the flow chart, but use the flow chart accordingly. So let's say, no, I'll write it out in words. How much no, how do I want to say this? Sorry. How many atoms of aluminum are in a 152.6 gram sample of aluminum? Okay, so how many atoms of aluminum are in a 152.6 gram sample of aluminum? I'll give you 2-3 minutes to work on that. Just another 30 seconds. Okay, so for this problem here, we're trying to find atoms of aluminum. So I want to find this area on the flow chart. I'm given grams of aluminum. Both are dealing with just the element. So I'm going to start here and I'm going to hop 2 hops to get over to my final destination. I'm going to write my given just to make sure it's all nice and clean. So given information is 152.6 grams of aluminum. And I'm trying to find aluminum atoms. So the first step is to go from grams to moles. Sometimes the moles are called like the crossroads in chemistry because you always have to kind of go through moles to get to the other end. So if we want to go from, we can even make a flow chart specifically for this problem, it's going to be grams of aluminum into moles of aluminum into aluminum atoms. So grams to moles is the molar mass. So we start with 152.6 grams of aluminum. That's our given. If I want to convert into moles, well, it's going to be moles of aluminum on top and grams of aluminum on the bottom, because I always want to get rid of the unit that's coming before, right? We want to get out of this and into this. What is the relationship between these two? Well, 1 mole of aluminum is the molar mass. So it's going to be what, 26.982. And a couple of those later decimals may vary slightly depending on the periodic chart you're looking at. No worries, it'll get you close enough to the answer. So that's our first step. That will get grams of aluminum out of there. The second step is to get into aluminum atoms. So here is mole on top. So I want to put mole of aluminum on the bottom. And I want to put aluminum atoms on top. Well, how does moles and atoms relate? 1 mole of anything, in this case, 1 mole of aluminum, is equal to 6.022 times 10 to the 23rd individual ones. This will allow the moles to then cancel. So anytime you're going from gram to mole, this is specific to whatever the material is, right? When you're going moles to atoms or moles to molecule, that is just a sort of standard relationship with Avogadro's number. So we're going to need to plug it into our calculator and we'll multiply across the top. So we've got that 152.6 and we're going to multiply it by 6.022 times 10 to the 23rd. And then we have to divide it by the molar mass, which was 26.982. All right, we get a large number, which we would assume we would be getting a large number. In this case, it is 3.406 times 10 to the 24th aluminum atoms. That's the only unit that's left. Good with that one?
Yeah.
Okay, let's do another one in this flow chart because you'll have a couple problems with this. So how many, what do we want to do now? How many grams of sulfur are in 16.4 grams of Fe2SO4. Okay, how many grams of sulfur are in 16.4 grams of Fe2SO4? So that one's going to require a little bit more work than this. You're given information about a compound. You're trying to find information about an individual element. So find your start and your end point on the flow chart and then set up your dimensional analysis. This one I'll give you about 5 minutes for. And Elizabeth, if there's anything specifically over the last two chapters that you feel like you want to go over, you can throw it in the chat or turn your mute off after we've gone over this, and I can go over specific stuff for you. Okay, so for this one, how many grams of sulfur are in 16.4 grams of Fe2SO4? So as far as the flow chart is concerned, we're starting here and we're ending here. So we need to go from grams of compound into moles of compound, then moles of element, then grams of element. We can't go directly this way. So let's start with our grams of compound and get it into moles of compound. So grams of Fe2SO4 into moles of Fe2SO4 into moles of just the sulfur into grams of the sulfur. So 16.4 grams of the Fe2SO4. 1 mole of Fe2SO4 is equivalent to the mass of 1 iron, 1 sulfur, and 4 oxygens. So it's got a pretty heavy molar mass, 399.88 grams. Oh, no, not that heavy. Scratch that. F2SO4. Let me just calculate it out here real quick. Sorry, I was just going to look it up online, but it's not coming up for me. 55. 2 irons plus 1 sulfur, 32.065 plus 4 oxygens. That didn't work for me, sorry. $207.8 grams of Fe2SO4. So now we need to get from moles of the compound into moles of the individual material. Well, looking at the formula, I get 1 sulfur for every 1 molecule. So it's a 1-to-1 ratio. 1 mole of Fe2SO4 is going to yield 1 mole of sulfur, a 1-to-1. It's not always 1-to-1, so make sure you're plugging in the number that is situated at the subscript. And then the last step is 1 mole of sulfur yields 32.065 grams. So grams of the compound cancel, moles of the compound cancel, and moles of the element cancel, and we should just be left with units of grams of the element, which in this case is sulfur. We've got our 16.4, we'll multiply it by that 32.065, and then divide it by the 207.8. And we get roughly 2.53 grams of sulfur. So in a sample of 16.4 grams of this compound, we should have 2.53 grams of sulfur. Any questions on that or how to use this flow chart? I think it's a useful thing to have available for you when you're taking your final. Okay. Other stuff you guys want to go over? Because I can go over more stuff from chapter 6, but if there's, there's quite a few other chapters. So I just want to make sure I'm going over things you feel good with.
Yeah, I think I wouldn't mind going over the molarity stuff, the the concentration, and then titration.
So solution stoichiometry?
Yes, yes.
Okay, let's do it. Now, know that, Elizabeth, the solution stoichiometry problems are pretty hardy, right? So you're probably only going to see one of those on the final. you're not going to see like 10 of them, you know? So we'll go over it. And if it's like, it's kind of one of those things where it's like, if it clicks, good. If it's taking you hours and hours to get it, maybe let it go, just because it's really only going to be a small portion, but we'll do a problem. How much, sorry, give me just a second. These ones are always hard for me to word. How many liters of a 2.5 molar HCl solution are needed to neutralize a 8.5 molar neutralize, I need to give you a volume. Neutralize, let's say, 6.0 liters of and we'll still go with that 8.5 molar NaOH solution. So it's a neutralization reaction between hydrochloric acid and NaOH. The equation for this would be hydrochloric acid plus the NaOH. And what are our products when we neutralize? We always get water is one of the things, and salt, which is just whatever's left over. So the Na and the Cl in this case, NaCl. It is a 1-to-1 ratio, so 1 and 1 here. All right, so I will give you all about 5 minutes to work on setting this up. This is the one where you want to figure out what's compound A, what do you have more information on, what's compound B, where are you trying to head, and then go from there. Obviously, I mean, there's only 2 of you, so if while you're working through it, if you get stuck on one spot, and you're like, I just need clarity on this one thing, just turn your mute off and ask me. Just another minute. Okay, so for this one, the general flow chart for this tends to be you go from the volume of your compound A into moles of compound A, into moles of the compound B, into volume of compound B. Sometimes you stop right here and then use that to find the molarity. How do we get from volume of A into moles of A? We use the molar, or we use, I'm sorry, the molarity. Molarity of A. Here we use the coefficients from the balanced equation. And then to get from moles of B into volume of B, this we use the molarity of B. And why do you use molarity? Well, because molarity equals moles over liters. It's a double unit, so you can use it as a bridge to convert between those two. So let's get compound A going, or let's classify compound A and compound B. Hey, Carrie. We're just working on some solution stoichiometry if you want to hop in at some point. And then if you have any questions too, you can throw it out there after we get done with this. So compound A is the thing we have more information on. In this case, it's the NaOH. What do I know about compound A? I know its volume. So the volume is 6.0 liters. And then the molarity is equal to 8.5 big M. Now remember from previous ones, always make sure this is in liter and get it out of molarity and into the double unit of mole per liter. So instead of 8.5 molarity, we're going to go 8.5 mole, specifically of the NaOH, for every 1 liter of the solution. Compound B, I don't know its volume. Volume is what we're trying to find. We're trying to get here. We do know the molarity of this thing though. It's weaker. It's 2.5 molarity. So 2.5 HCl specifically. So I'm going to convert that again right away into moles per liter. So 2.5 moles of HCl in every 1 liter of the solution, specifically the HCl solution. Looking at this, I can see that I'm going to need a larger volume of this to neutralize this because I know it's a 1-to-1. So I expect this to be a bigger volume than the 6 liters. But when we're going through this, start with volume A. So we're going to start with this 6 liters, convert into moles, then go to moles of B, and then volume B. Let me just start that out. This takes up so much space. So we've got 6.0 liters specifically of NaOH. I'm going to use the molarity to get into moles. I want moles, I don't want liters. So I like how this is set up just like this. So I'm going to put the 1 liter on the bottom and I'm going to put the 8.5 moles of NaOH on the top. That's going to get rid of my liters of the NaOH solution. From there, I need to get from moles of A into moles of B, or moles of this into moles of HCl. That comes from the balanced chemical equation. It's not always a 1-to-1. In this case, it does happen to be one of those produces one of those. Usually with your titrations, you guys have probably seen it's been 1-to-1. So 1 mole of the NaOH will produce 1 mole of the HCl. From here, I want to go from moles of compound B, which is HCl for this problem, into volume of B, and I need to use the molarity. So here's my molarity. Do I want to use it this way? No, because I want to keep the unit of liter. That's where I'm headed. I want to get rid of the unit of mole, right? Here's mole of HCl. So I need this to flip-flop. Or I need to use 1 liter of HCl over 2.5 moles of HCl. Remember, these are conversion factors. It's a 1-to-1 ratio, so we can always flip-flop them. So I'm going to take this and stick it in over here. So 1 liter, I want that on top, 1 liter of HCl for every 2.5 moles. Oh my gosh, that is atrocious. Hold on, clean that up a little bit. 1 liter of HCl for every 2.5 moles of HCl. You just check and make sure that things have canceled along the way. So moles of NaOH and moles of NaOH, moles of HCl and moles of HCl. So then we plug it in our calculator and we're going to take anything that's numerically not 1 and multiply it together. So the 6 times the 8.5, the rest of them are 1s, so I can ditch that. And then we're going to divide it by 2.5. We end up getting a value of 20.4 liters, 20.4 liters of HCl. I guess I would round this to 20 liters of the HCl solution. So I need 20 liters of the HCl solution, which is a lower concentration, to neutralize 6 liters of this higher concentrated NaOH. Elizabeth, how was that?
Yeah, that's great. Thanks. I just needed to go over it one more
refresher.
time. Yeah.
Okay, yeah. So again, are you going to see this like all over the exam? No, you might see one of them. All right, so don't stress too much about it, but you have the notes available. Other stuff you guys want to go over from the last 2 tests? I'm trying to think what, there's balancing chemical equations. There was, Elizabeth, looks like you've got something.
Yeah, I think the square with the pH and the hydronium and because I did some, I guess I'm a little bit lost on the OH side of the square.
Okay. Yeah, we don't use OH quite as much just because everything seems to be in pH, but we can play around with that. So what did we do here? We had the H3O plus over here. We put the OH minus over here. We put pH here. We put POH over here. This was the relationship between KW, which equals the OH. I'm going to put the H3O plus first. H3O plus times OH. Over here, this one, POH equals the negative log of the OH concentration. Or we can use the other equation that tells us that the OH concentration is equal to 10 to the negative POH. These are inverse of each other. Here, we've got pH plus POH will always equal 14. And then here, these mirror what these things say over here. So pH is equal to the negative log of the H3O plus, and the H3O plus concentration is equal to 10 to the negative pH. We can mess around on this side a little bit. So let's say, okay, what is the POH of a solution with an OH concentration of 6.3 times 10 to the negative, 10 to the negative 5 molar. What is the pOH of a solution with an OH of 6.3 times 10 to the negative 5 molarity? Okay, also let's say, what is the pH And then tell me, is it acidic, basic, or neutral? Okay. You can do this problem. You can get through probably all of the pH calculations. So I'll give you a couple minutes to do it. Solve these in order though. I think that will get you, your results will kind of just stack on top of each other. I'll give you 3 minutes for that. Okay, so when thinking about POH, it's sort of the inverse or the opposite of pH. pH is giving you an idea of the hydronium concentration or the concentration of the acid thing. It's in reference to the acid or the H. POH is like pH, but instead of talking about the acid, it's all involved in what's happening with the concentration of the base. POH is like, you know, if pH is 3, the POH will be 11 because of this relationship with them being both equal to 14. So as one of these is down, the other one is up because this is talking about the acid, this is talking about the base. So with this problem, what is the POH of a solution with an OH concentration of 6.3 times 10 to the negative fifth? So we have the OH. We're going to try and calculate the POH. That's the first step here. So we're going to go from here to here. Now we know POH is equal to the negative log of the OH concentration. And I'm just going to insert it right in here, this 6.3 times 10 to the negative fifth. So our POH, is 4.2. Now, some people may look at that and think, oh, this is acidic. It's not actually, because we're talking about the POH. That's why I said wanted you in the second part to say, hey, what is the pH? Let's get it into pH, because pH is the one that's the lower it is, the acidic. On POH, the lower it is, the more basic it is actually. So scratch that. So let's find pH. So pH is going to equal 14 minus this 4.2, which gives us roughly 9.8 for the pH. So now we can conceptually start thinking, is this acidic, basic, or neutral? On the pH scale, if you're larger than 7, you're basic. This is definitely greater than 7. So we're going to go with basic. Elizabeth, how's that? Enough
Yeah,
refresher?
I get that pretty well. Yeah, it's yeah, that's fine.
Okay. Do you need more, or you feel okay with that, or?
No, the problem I was having was doing the negative log to the pH or the POH, depending which one you get. And then, so in some of the homeworks, I would put the answer the way that you showed us how to do it, with the pH is the negative. Wait a minute, is that right? The pH is the H3O is the to the negative pH, right?
10 to the negative pH.
Right, and so I was inserting the answers that way.
Mm-hmm.
But then it would come up with a number value, which I was like, I know that there's some simple thing I'm missing here.
So let's say that the pH, because I think I might know what you're talking about. Let's say the pH is equal to 3.5. So you were plugging it in like this, 10 to the negative 3.5.
Yes, that's right.
Okay, I want you to actually plug this into your calculator and see what number comes out. Because we don't really like to have our exponents in like decimals like that. So what you're going to want to do is plug it into the calculator. So take, 10 to the negative 3.5. Did you get 0.003162?
Yeah, I get that. I don't know why that was tripping me up so much, because that's real simple when you put it out like that.
Yeah. And then I'm going to put it 3.16 times 10 to the negative what? 1, 2, 3, 4 to the fourth. Because we get used to like preserving our exponent, right? But when we have the exponent as a decimal like that, we do want to work that out in the calculator. If it was, let's say instead of that, let's say the pH was exactly right on the now 4. Okay, well, that would be 10 to the negative 4, right? Or we would probably write it as 1 times 10 to the negative 4. I know it's like more characters than it is here, but when it's a whole number, you can kind of write it like that. When it's decimal, you need to work it out.
Okay, so on the test, it's probably not going to be concerning the POH then, just the pH, or?
Yeah, I mean, for the final, I don't really remember. I think I don't fully remember. I mean, I would know how to do it in either one. Just know if they're giving you information about OH, you need to use, POH stuff. If they're giving you information about the H3O plus, you need to be doing pH stuff. You don't want to use this information in this equation over here, or this information in this equation over here. Okay, Okay, other questions or areas that you want to just go over so you don't have to study solo alone by yourself over the weekend?
Can you just complete the rest of that square and do the, I mean, I know we said it's basic because the pH is 9.8, but then when you
Mhm.
get up to the top of the square and you're doing the KW constant, I mean, I'm pretty sure I understand how that works, but would you just go over that one more time?
You want to go between these two?
Yeah.
Okay, yeah. So let's say solution has a concentration of OH at 3.4 times 10 to the negative ninth. What is the H3O plus concentration? (3.4 times 10 to the negative ninth). Sorry. I'll give you, I don't know, a minute and a half, 2 minutes for that. Oh, and if you don't know the KW constant is 1.0 times 10 to the negative 14. Yeah, but you kind of need that to do the equation. Okay, so anytime you're going between the H3O plus concentration and the OH minus concentration or vice versa, you can use this simple equation. We want to find H3O plus. We want to find this thing. So let's move the OH to the other side. So the equation should work out as the H3O plus concentration is equal to the KW constant, which is 1.0 times 10 to the negative 14, divided by the OH concentration. These can get flip-flopped. So if instead of finding H3O, you wanted to find OH, OH would equal the KW constant divided by the H3O plus. You just swap places on those two things. But we want to find we want to find H3O plus. So let's plug it in, 1.0 times 10 to the negative 14 divided by whatever our OH was that we said was 3.4 times 10 to the negative 9. I can already tell that this is less, this number is smaller than the 7, the negative 7 cutoff. So there's less base than there is, it's going to be acid. And we'll plug it in to get that actual number. So get 2.9 times 10 to the negative, what, 1, 2, 3, 4, 5, 6. 10 to the negative 6. Yes? No?
Yeah.
Okay. So when looking at these two things, if there was an additional question in here that said, hey, is it acidic, basic, or neutral? Well, who's winning? This is the H3O. This is the acid thing, right? And this is the base thing. What number is bigger? This is the bigger number. The acid wins. So we would say it's acidic.
Okay, I must be entering something in my calculator wrong because I am not getting that answer.
You're not getting that answer?
No,
What calculator are you using?
I'm on a TI 84.
Okay. Are you putting parentheses around these?
Oh, no, I didn't. Okay.
So try that out. Yeah. And then see if.
Right. I think that's what I was doing too.
Yeah, because what will happen if you just plug it in like this and you don't use parentheses specifically on this bottom thing, it's going to take this number, it's going to multiply it by this number, it's going to divide it by the first part of this number, and then it's going to multiply it by this number, and it won't give you the same exponent.
Okay.
So yeah, try it again and see if it gives you what you need. One way to work around that, use the EE button. So 1.0 EE negative 14 divided by 3.4 EE negative 9. Or so, instead of EE, sometimes it's E. Is that working for you, Carrie? Okay, good. All right. Other things? You will have to balance some chemical equations. Feel good with that? Yeah. No. You will have gas law stuff, which is really just sort of plugging and chugging. Solutions, acids and bases. That acid base chapter, a lot of that outside of this is very similar to the solutions chapter with the solution stoichiometry. Hold on, I'm going to stop sharing my screen for a second. Take a peek at something. You think of something, you just shout it out. Otherwise, I'm going to just sort of take a peek and see if anything sparks my interest.
So you have all of the other lecture videos up already though?
Yeah, they should, everything should be up.
Okay.
If for whatever reason you're having trouble with it, let me know.
I think that was everything I had questions about.
That was everything.
But
Okay.
you know, just so long as you have the videos up in case I need to go
Yeah.
back and watch.
How did you guys feel about doing one thing that I see people have trouble with, calculating empirical formulas from like quantity amounts? Remember, like, hey, it's 33% carbon and 22% oxygen. What is the empirical formula? You want to finish up with one of those?
Yeah, that wasn't really my favorite thing, but yeah.
Well, you're gonna have one of them on the final, at least. Probably one, but wasn't my favorite thing. I appreciate the honesty. Physics was not my favorite thing in school. That was the one class that I just hated with all my might. And now I like it, but I did not like it in college. All right, let me come up with one. My screen, share my screen with you all again. Okay, so what is the empirical formula of a compound containing 43.7% phosphorus, repeat, and 56.3% oxygen by mass. So do one that just has two different things. So we're at 10:34. I'll give you guys like 4 minutes to work on it, and then we'll go over it. You're like, where do I start? Well, remember, percentages can be thought of as grams. Grams needs to get into moles, and then find the ratio from there. Just another 20 seconds. Okay, so the empirical formula is the lowest ratio of the subscripts, specifically lowest whole number ratio. So the system that you're going to follow when you've got percentages of each, take the percentage and just assume 100-gram sample, and we can just change that to a gram. So I've got 43.7 grams of phosphorus and 56.3 grams of oxygen. Because if I had a 100-gram sample and it was by percentage, that would in fact be true. That would be the correct mass ratio. Now, when we're writing a chemical formula, because what we're going to try and do is write a formula that looks something like PXOY, and we're going to fill in numbers for the X and the Y. This relationship, so how many phosphorus we have to how many oxygen we have, is a molar relationship, or it's an atom relationship. It's not a mass relationship. So I need to get out of grams. So instead of being in grams, I'm going to go to moles. So 1 mole of phosphorus, how many grams is that? You use the molar mass to convert it into moles. So it's 30.974 grams. Now we'll have a unit of mole, which we can actually plug into our formula. So this is going to get a value of 1.41 moles of phosphorus. We do the same thing for each individual compound. If you have 2, you do it for 2, 3, 3, whatever. But you use the molar mass for each individual one. So this is phosphorus, this is oxygen. So instead of using phosphorus as molar mass, I would use obviously oxygen's molar mass, which is 16 grams of oxygen. In this case, and then grams cancel and you're left with moles. So I get 3.52 moles of oxygen. So this is the correct ratio. What don't we like about this ratio? It's not a whole number. So we need a kind of a trick to get it into whole numbers. The text teaches you to put this into a skeletal formula with these numbers as the subscripts, or you can do it divided out at this point here. I'm going to put it in as the subscript. So P will have this subscript 1.41, and oxygen will have this 3.52. So this, again, it's a correct ratio. It's just not a whole number ratio. So the fastest way to get a whole number ratio, divide both of them by the smallest decimal. So we divide it by 1.41, and we also divide this one by 1.41 because it's the smaller of the two. So that leads me to phosphorus having a subscript of 1, right? Anything divided by itself is 1. And then oxygen has a subscript of 2.5. So we hope after this step we get 2 whole numbers. Did we get 2 whole numbers? No, we didn't. If this was like 2.999, we could round that to 3. But if it's 2.5, that is not close enough to round. So what I need to do now is multiply both of these subscripts by a number that will get them to whole numbers. If it's 0.5, you multiply by 2. If it's 0.3, you multiply by 3. If it's 0.25, you multiply by 4. If it's 0.2, you multiply by 5. You multiply by whatever, we'll get rid of that decimal. So I'm going to multiply both subscripts by 2. That will get me phosphorus with a 2 and oxygen with a 5. This ratio is the same as this ratio and is the same as this ratio. It's just this ratio is whole numbers, and we like whole numbers. We don't like decimals. So grams into moles, divide by the smallest decimal. Hope you get a whole number. If you don't get a whole number, you multiply by a number to get it into whole numbers. And that's how you do it. Okay, so we've got 3 minutes left. Any last burning questions? No. All right, well, this is our last lecture together. So you all have been awesome, all 3 of you, and the people that aren't here. You guys have been awesome. Carrie and Elizabeth too, I really appreciate you being the strong ones to keep your cameras on for most of the lectures. It is really, really helpful for me. Just know that moving forward too, it's really helpful for your instructors when they can see a face. It lets me know like, oh yes, okay, you're getting this, or no, you're not getting this. Or at least I know what Carrie and Elizabeth have been getting and not getting. So thank you for that. I really appreciate that. Yeah. if you have questions on grades and stuff like that, try and get it to me before or sooner than later. I have to have your grades in by Tuesday morning. So that's why you got to get that final done ASAP. In actuality, I want to look at, because part of me thinks your final is only open until 5 on that Monday. Usually you have till midnight, right? I think you guys only have till 5. No, it looks like it's still open till midnight. Okay, you should be fine. So Sunday to Monday. Oh no, it's my 1:30 class. They have to take it on Tuesday. So yeah, you've got 3 hours to complete it. That should be more than enough time. If you have questions on other parts of your grade, let me know sooner than later. I have a couple more 2 labs I need to grade for y'all. I'll try and get those done by Friday. And then I've got to input your mastering chemistry homework. The mastering chemistry is going to be, as long as you've been doing it, it will be pretty lenient on the points that you get for it. All right, it's sort of a participation grade on that. So yeah, bye everybody. If you guys are here in fall, come see me in my office. I'd like to meet you in person. And if you want to take 1:30 with me, I'm teaching it in fall.
Awesome. Hey, will you post this lecture so I can see what I missed?
Yeah.
For
Yeah.
30 minutes.
I'll do it right now.
Okay, thank you.
Thank you.
Yeah, thank you, Evan. Bye, Elizabeth. And Carrie.